Okay, so the next one is 13. Here we have two distinct odd prime numbers p and q such that p minus 1 divides q minus 1. Also, there is another integer a which is relatively prime to pq. Then we have to show that the q minus 1th power of a is congruent to 1 modulo pq. Solution: we will start with this condition and the distinctness of p and q. Since p and q are distinct and a is relatively prime to pq, a is relatively prime to p as well as q. Okay, so by Fermat's theorem, we will get these two congruences. And now we use this thing, p minus 1 divides q minus 1. Since this, we have q minus 1 some multiple of p minus 1 for some positive integer k. Alright, so now if we raise both sides of this congruence to their kth power, which we can do because k is a positive integer, we are going to get this. A to the power q minus 1 is this, which is, which can be written like this. So here our modulus is p. We are going to write it finally, but it is p. And that's why this thing is congruent to 1. So this is congruent to 1 to the power k, which is just 1 mod p. So now we see that the q minus 1th power of a is congruent to 1 modulo p as well as modulo q. And now you use the fact again that p and q are distinct, since these are distinct primes, so they are also relatively prime. Hence, you can now write that same congruence, but this time the modulus will be pq. And you already know the reason, because if you write in place of this congruence the corresponding divisibility relation, it tells us that p divides a to the power q minus 1 minus 1, and q also divides that thing. And because P and Q are relatively prime, so their product will also divide that difference, which when you translate back as a congruence, you get this. So this is what we wanted to prove. Next, 14. Again, we have distinct odd primes. If P and Q are distinct odd primes, prove that P to the power Q minus 1 plus Q to the power P minus 1 is congruent to 1 modulo PQ. Okay, so let's see the solution. Since P and Q are distinct primes, so they are also relatively prime. So we can now apply Fermat's theorem twice, once with the modulus P and the other time with the modulus Q, and the basis will be Q and P. We will change that like that. So by Fermat's theorem, we are going to get these two congruences. Mod Q and mod P. Alright. Now these congruences further give us these two congruences. Now we are going to consider this number. Let us first think of the modulus P. Because P divides this power of P, so this power of P contributes 0 to this sum when we think of in terms of congruences. However, this power contributes 1 to the sum because of this second congruence. This means that this will be congruent to 0 plus 1, that is 1 modulo P. And similarly, if the modulus is Q, then Q divides this second term, so the second term contributes 0 because of that, and the first term from this congruence contributes 1 to this sum. So that way we again get 1. And now you again recall this thing. Since P and Q are relatively prime, we finally get what we want. Let's do one more. 50. Establish the statements below. Okay. There are two statements. If the number MP, which is 2 to the power p minus 1, is composite, where p is prime, then MP is a pseudo prime. Let us first prove this and then we will see part B. So we need to now recall the definition of a pseudo prime. Let's recall that a pseudo prime is a composite integer. Okay. Positive, of course, we are only talking about positive integers. A composite positive integer n is called a pseudo prime if n divides 2 to the power n minus 2. We want to show here that MP is a pseudo prime. It's already given that MP is composite, so that part is already there with us. So we now have to simply prove this. Okay, so let's see how we can do this. We will have to start by using Fermat's theorem with the prime p as our modulus. Fermat's theorem means actually it's corollary by Fermat's theorem. We have this, right? That is, so this is not exactly the statement of Fermat's theorem. The statement would have been 2 to the power p minus 1 congruent to 1 modulo p provided p does not divide 2. But we don't need that. We need this one, and this congruence is true regardless of whether p divides 2 or does not divide 2. Okay. Now we write it as a divisibility relation, that is p divides 2 to the power p minus 2. Now at this stage we need to recall the result of an exercise which we proved long ago, and we have already used that exercise many times. Many times means 2 or 3 times. That exercise is this: say n is a positive integer which is divisible by another positive integer d. Then 2 to the power d minus 1 also divides 2 to the power n minus 1. That thing we are now going to apply here with p in place of d and this thing in place of n. And the result is exercise 21A of section 2.2. By that exercise. So if we apply that, what shall we get? 2 to the power p. So we raise 2 to this power, pth power, and from that we subtract 1, and that has to divide this. I should have already done something here. I can do it here also now. You note one thing, that MP is 2 to the power P minus 1. So if I subtract 1, another 1, then I will get 2 to the power P minus 2. That means this number is MP minus 1. So here I can now write, instead of writing this exponent, I can write MP minus 1. You see, so many bases and exponents and suffixes are there. You should not get confused. From MP we are subtracting 1, not from P. Okay. And from this entire thing we subtract another 1. This is what we get. However, note that actually MP itself has appeared here. So MP is dividing this number. So obviously MP will also divide twice of this number. MP divides this. And if you do the multiplication, what do you get? 2 to the power MP minus 2. This is what you wanted to show, right? Combine this with the given condition that MP is itself composite. So now you have proved that it's a pseudo prime. And now we see part B. Every composite number of this form Fn, which is 2 to the power 2 to the power n plus 1, is a pseudo prime. I think these numbers are called Fermat's number. That's why Fn, if I am remembering correctly. Okay. And here also we are going to start by applying this exercise. To what? To which divisibility relation? To this. Since 2 to the power n plus 1 divides 2 to the power 2 to the power n. Okay, but before we do anything else, why is this true? You see, the dividing number has less number, it's a power of 2, that one is also a power of 2. Here there are less 2's and there are more 2's. The number of 2's in this power is 2 to the power n, whereas the number of 2's in this power is only n plus 1. And if n is a positive integer, which is understood, I mean there is no need to write that, n plus 1 is less than 2 to the power n. So obviously if there are more 2's, you can divide this one by this one. That's a simple fact. Okay, now we need to be very careful because already there are so many powers of 2's and also iterated powers of 2. And yet we are even going to consider more powers of 2. 2 to the power. So the exponent now will be this. That is 2 to the power 2 to the power n plus 1. And from this entire power, we subtract 1. And that will divide this number 2 to the power 2 to the power 2 to the power n minus 1. This minus 1 is from this entire big power, not from that one, not from that one, okay. However, this number itself can be written like this. It can be written in terms of Fn. So what is our Fn? Fn is this plus 1. Here if we had a plus 1, we would have written Fn here. That means this exponent alone is Fn minus 1. Minus 1. Okay. Now let's again consider the number Fn itself. So what is Fn? Fn is 2 to the power n plus 1. And this of course divides its own multiple by this other number. Because only this much is Fn, so obviously this divides this. However, it's in the form a plus b times a minus b, so you can apply your usual a square minus b square formula. If you apply that, there is such a high chance to do something wrong here. So many exponents, so many levels. Now what will you write here? By the laws of exponent, you see, if you multiply this 2 and this n, then it's wrong. Because this is basically a power of 2, where the exponent is 2 to the power n. With that only you have to multiply 2. So if I write one more line, it looks like this. And that's why, and here in the exponent itself you can apply the law, one of the laws of exponents, and write this as 2 to the power n plus 1 minus 1. Alright, so now you look at this and this. Fn divides 2 to the power n plus 1 minus 1. Which however itself divides this number. So obviously, because divisibility relation is transitive, so Fn will divide this number, minus 1 minus 1. And this further implies what? That Fn also divides twice this number. Again, like before. But twice this number is nothing but 2 to the power Fn minus 2. So it was given that this is it was not given, the condition is that if for some n this is composite, then it will be a pseudo prime. Because in any case, Fn is dividing 2 to the power Fn minus 2. So if Fn is composite, then it's a pseudo prime, and that's it. So let me just end the video here itself. And what shall we do tomorrow? Tomorrow is Tuesday, no? On Tuesdays, what we do? Oh, okay. Topology, I think. Yeah. So let's do topology tomorrow. So see you tomorrow. Until then, this is me, Lucifer from A Mathematical Room. Have a nice night.